welcome our next speaker, Professor Mahendra K. Verma from the Indian Institute of Technology, Kanpur. Professor Verma's talk is titled Surprises in Euler Turbulence, Emergence of Order in 2D Euler Turbulence.
Thanks, Manisha, and thanks to the organizers for this invitation. It's a nice conference. I'm a physicist, so the maths here is pretty low level math, so that apology to mathematicians. So this work is done in collaboration with two students. Somdeep is here, and this person has gone as a postdoc elsewhere. So I just want to start with this statement that turbulence normally we think of as a non-equilibrium system, but we are looking at equilibrium aspects of turbulence. Okay, I will make it clear as we go along. It's in Euler equation. So this is just advertising my book. So some of the stuff I'm talk today will be from this book, Energy Transfer book. This paper is published. What I will talk today is basically in this paper, and this this paper, and this is a preprint. So everybody knows Euler equation, so I don't need to spend time. So one thing to notice is I'm going to talk like a physicist. So there's no force and there's no dissipation. So we expect no heat generation. So delta S, the entropy change, which is proportional to delta Q, which is heat generation, is 0. So entropy should not change. This is thermodynamic entropy. So we expect, how to quantify order if the entropy is not changing with time. So that's where we say, well, things are, you'll see, well, I'm sure everybody knows about it, the order of Euler turbulence changes with time. So then we want to quantify that order. So we're going to do some trick with that in a while. So entropy is constant. It is there in Landau's book and everywhere. So that's for Euler turbulence. And here I mean thermodynamic entropy. Okay. So let's look at equilibrium solution. It was proposed way back in 52 and 73. T.D. Lee, the particle physicist, and Khanin. So the proof is a bit complicated, but I'm going to give a very simple proof to look at that equilibrium solution. So we can start with the white noise, this white noise, okay, and this white noise. So velocity field is a white noise, okay, and it's incompressible. We make it by a trick. So please believe me that it can be made that way. So if I take Fourier transform of this, I'll get a constant energy for each mode. So K is the Fourier mode. So energy is equipartition among all the modes, and this is a solution of the Navier-Stokes of the Euler equation. And so from this we can get each mode is constant modal energy. So the energy in 3D will be K squared, and energy in 2D will be K, and that is what well. This is one simple form of Khanin solution. Khanin puts in helicity in 3D, so that makes it more complicated, but the basic idea is basically this. Oops, what happened? Went too far ahead. Yeah, so this is the Khanin solution. It's more complicated, but you can see that if gamma is 0, then we get K squared and K in 2D. With gamma is connected to kinetic helicity, which we will ignore in today's talk. Essentially, some of my plots will have some gamma effect, but not so critical. So this paper has been cited by almost all the talks. 1949 paper by Ansager. So I just want to say a little bit about this paper. This paper does show large-scale structures or the vortex structures in Euler turbulence. It's very well. Normally, it has been talked about the Ansager criteria for regularity of Euler solution, but in the beginning he talks about 2D turbulence. And so 2D turbulence, he assumes delta point vortex and collection of point vortices. And in fact, this paper, I think probably for the first time, he talks about negative temperature, and that happens because of the volume of area of the box is finite, and in finite area we can get negative temperature. So I'm just going to give a glimpse of what he's talking about. This is from Wikipedia. For Ising systems, for low energy, the spins are all aligned along the magnetic field. For higher energy, then they are basically become random. But if you increase even further energy, then they get anti-aligned, right? Because energy is too much, so it's anti-aligned, and energy is basically anti-aligned here. So it's ordered here, and even also for very large energy, it's ordered. So that's what happens for, so if you put in more energy or high temperature, is ordered, and this part, entropy, is decreasing with time, decreasing with energy. So here it is going to be negative temperature. Delta S by delta E is 0, negative delta S by delta E, so a negative temperature. And this is from this paper, that for small temperature, we get vortex and anti-vortex. These are blue and red are vortex and anti-vortex. They are coupled, but for very high temperature, lot of clumping of positive vortex and negative vortex, they clump together. And this part is like negative temperature. That's what he talks about. So the point to notice here is that if you have very high energy state, it's getting ordered. That means normally we think that if you put very high temperature, it should get disordered, but that doesn't happen for Euler. And I think that is what we'll see some of it in our simulations. So this is, in fact, has been verified. Well, it has been seen in quantum fluids as well, superfluid. In fact, this paper is talking about this stuff in Bose-Einstein condensate, the superfluid, and okay. So numerical simulations. So let's see whether we can get equilibrium solutions and non-equilibrium solutions, if at all. That's what we'll target. So we'll use the Côte Tarang, and we'll use a slightly different time stepping scheme. It's not Runge-Kutta, because Runge-Kutta does not conserve energy. But so we need a sophisticated numerical scheme called PFRL scheme. It conserves energy up to 8 or 9 decimal places. So for 3D, in fact, it's trivial. 3D is not so interesting if you're looking at equilibrium or non-equilibrium solution for Euler. But please keep in mind, it's a truncated Euler. It is not like what Takasi was talking about. So we are simplified physics model we are discussing here. So this is one snapshot, a cut of a cross section of a 3D box. The color is vorticity, vertical vorticity of the cut, and these fields are basically the velocity fields. And this looks random, right? This is a steady state. If you wait for some time, and steady state, and this profile for velocity field probability distribution is Maxwellian. So it's convincing that this 3D flow is in equilibrium, following Khanin and TDL. So it is following that idea. We can look at the energy flux. So energy flux, I'm sure everybody knows about it, but is energy coming out of a wave number sphere of radius k0 by nonlinear interactions. And for equilibrium solution, this should be 0, because the detailed balance will be respected. For 3D, energy flux, which is sitting here, is 0 for both 2D and 3D. But spectrum Ek by k squared is flat. This is because of helicity, which we'll ignore right now. So it's verifying Khanin's idea. A detailed balance is respected. Great, everything is looks in nice form. For 3D non-equilibrium solution. So non-equilibrium not all the way, but in the beginning there's non-equilibrium. Then it becomes equilibrium after some time. So it's evolution. So I want to make a remark. For the previous slides, we use random initial condition, that white noise initial condition, and it remains there throughout. Okay, but we start with an initial condition which is not random. So we can look at our initial condition, which is Taylor-Green vortex. So it's a section. So we are not showing 3D box, but it's a section. So there are 2 pairs of vortices sitting here, and this is a t equal to 0. But at later time, t equal to 60, it has become almost random. So it took some time, but it became random. So this is, so our final state, of course, depends on the initial condition. If you look at the energy spectrum, then in the beginning we get in fact, it's a delta function here in K, but later on it becomes K squared. The blue line is a K squared. The flux, in the beginning it is non-zero, but finally, well, there are some fluctuation as large K, but it's essentially zero for this system. So the system has thermalized. That's a word which is used in statistical physics. It has become like thermodynamic gas. So initial condition matters, and the spectrum. This is by work by Brache's group earlier. So I cited it below. But so the thing is, interestingly, we get 5/3 spectrum and then K squared spectrum. This K squared is what is Khanin solution, and this is Kolmogorov solution. So this system, in some sense, is both in equilibrium and non-equilibrium in the intermediate stage. So, I mean, it's nice to see that one system can have equilibrium components and non-equilibrium components. I will come to it a bit later, this aspect as well. So in fact, we can think of viscosity. This thing is playing a role like a viscosity starting from here. Now, it turns out quantum systems, there was a talk last month. A quantum system also seems to have some certain similarity. Quantum systems are Hamiltonian systems. Okay, if you don't put a heat bath connection, and that system too thermalizes. So there is a connection. In fact, people are exploring this connection. So let's look at 2D Euler. Now, for random initial condition, if we start with white noise initial condition, then we get this solution, which is every mode has same energy, great, and the flux is zero. Expected Khanin's solution way back. But what if we give some kind of ordered structure in the beginning? Then are we going to get to the solution like 3D or not? There is quite a bit of work in this field, but there are papers which are kind of non-committal. This is, well, maybe equilibrium, maybe non-equilibrium. This has been going on for a while. So let's look at it from numerical point of view. So this is an important slide. I think we need to just spend a bit of time. So we start with 3 initial conditions. So run A, run B, run C. And these are set of vortices. In fact, many of them. It's a 10 by 10, 100 vortices here. This one has less number of vortices, but we put interaction among them. So there is always interaction which is coupled in this initial conditions. And this is basically 3 modes we put, 1, 0, the Fourier mode, 1, 0, 0, 1, and 1, 1. Now we evolve this in time, and we run it for a long time. This is run by Somdeep last, in fact, some of these results came last week. So here we get not a random thing like what we saw in 3D. This is a pair of vortex. There's just one vortex and one anti-vortex sitting here. Well, this here there are 2 pairs of vortex and anti-vortex for this initial condition. And this is a shear layer, also has vorticity, but it's a shear. So for these 3 runs, we get different asymptotic state. And believe me, these are, well, we are quite confident, 99%, that these are the asymptotic state. It's not going to disappear to random after 2000 times or 3000 times. So that is what we believe. Of course, 99%, 1% is a chance that it may go away, but I don't think so. So to convince you that this is a time series only till 30. 1000, basically, we took a mode, a most dominant mode, and its energy is fluctuating a bit, but it's nearly constant. So that means it is asymptotic state, which is not equilibrium state. So a movie which was made by Somdeep. So let's just play this. So this is one vortex and one anti-vortex. They are just moving around, and this is time is 800. So this is a late time. So it is basically unsteady flow. So I mean, statistical physics, people normally believe, this is not a proof, but it's belief that many body system or many degrees of freedom system should thermalize. And this is one exception which is not thermalizing, and that's the interesting part of this problem. So we look at the energy spectrum to verify whether Khanin solution is matching or not. We don't expect it because it's not really equilibrium visually. So it turns out that these for 3 different runs. Spectrum, the dashed line is a fit to Khanin spectrum. Of course, we have 2 parameters, beta and gamma, and we do a fit. You find that these 3 runs, the fits are, it does fit with this still k equal to 10. This is a 10, but this part is not fitting. The low wave number modes are not fitting with the Khanin prediction. You look at the flux. Flux has strong fluctuation. In fact, these are for 3 different runs, there are 3 different colors. They are fluctuating quite a bit. It's not going to 0. So there's a lot of exchange of energy among the Fourier modes, and it is signature that it is non-equilibrium. This is what we are getting here. So this is a given snapshot. We get basically non-zero fluxes here as well. So we can do it, of course, when I say, well, we are averaging it, then it's showing something else. The single snapshot, how does it show? So we looked at it from different point of view, and we find that the flux is definitely non-zero for this system. And also, if you look at the lower wave number modes, and these are deviating from Khanin prediction, and these fluxes are again non-zero. So one more way to look at this system is that we look at this energy equation. In fact, it has appeared in several talks before. D by dt of a Fourier shell, one shell. So this is the transfer term. Yeah, so there's no viscosity, there's no forcing, so this is the only thing. Now, for equilibrium, we expect Tk to be 0. That's what we expect. But for this case, Hamilton system, we should expect to 0. But for 2D Euler turbulence, we find that these are non-zero. So these two are equal. It better be equal because of this. But both these terms are fluctuating. And this amplitude is reasonably large. So this is another signature that the system is not in equilibrium. Of course, we can look at it from phase space perspective of ergodicity, what we should target, but the test is not so easy. This is a large degrees of freedom, but this appears to be a good test, and this is a nice way to see it. I just want to make a remark. In this paper, we looked at KdV equation as well for this system. For soliton, which is an ordered structure, we expect that this Tk should be non-zero for soliton. But it turns out for soliton, this is 0. Soliton, single soliton, the ideal soliton, is the equilibrium solution. That's what we try to argue. We showed it numerically. Well, in fact, analytically, that solution we can find Tk, and this is interesting thing. So it's not necessary that for equilibrium things should be random. Even ordered structure can be in equilibrium by this definition. Now let's. So the summary of this part is that 2D Euler is not thermalized, even though it is an isolated system. It has no energy input from forcing, no viscosity. It is out of equilibrium. And quantum systems, I think, there are a lot of activity, so that connection would be nice. Okay, now, so you see, order of the system was changing with time. In 3D, it was getting order to disorder visually, and in 2D, also things were changing in time. But entropy is constant. Now, of course, we say thermodynamic entropy is not simply order. Thermodynamic entropy is more complicated object. But let's see whether we can quantify this order by some other measure, which could be a non-equilibrium measure. So we said, well, let's coin something. Let's look at some formula. And it's not a new formula. In fact, there are. Oops. I pressed the wrong button. Okay, so this has been, we follow Shannon's formula by the following manner. So this part, so I want to motivate this. I have enough time, so I just want to motivate this. So we want to contrast two different systems. I think it's important to look at the schematic. So we have a ideal thermodynamic gas. This is a set of particles which are randomly moving, and we got it here. And this is well developed starting from Bozeman, Gibbs, Stalwarts. So they have given the formula for entropy, entropy change, and so on. But just let's change the system a bit. Along with this random motion, we are going to give a certain coherent motion to the molecules. So imagine the gas, our atmosphere. Atmosphere, each molecule has a mean velocity or certain advective velocity plus random velocity. In fact, for the atmosphere, the mean velocity is much slower than the thermal speed. Okay? So in fact, in the real system, at least the gas in this room itself, it has two components. One is hydrodynamic component and other one is thermodynamic component. And hydrodynamic component has its own dynamics, like energy flux is there, this Kolmogorov flow, Kolmogorov energy flux. So this part, hydrodynamic part, cannot be captured by this formulas, entropy. So in Euler or Navier-Stokes equation, I believe that there is a thermodynamic entropy, which is of course coming from the small scale thermodynamic motion. But what about order of the large scale structures? We don't really talk about it, but I think we should think about that entropy, order of the vortices of the atmosphere or the fluid flows. And this could be a good candidate. So it's bit conjectural. So we define probability of wave number k as energy spectrum, modal energy divided by E. Okay, and sum of pk will be 1. Now we can define following Shannon, S as minus pk log pk, we're summing over all the modes. So this is a measure. And so it will capture macroscopic order even when dissipative systems are there. So these two, in fact, for hydrodynamic flows, I think we need a combination of these two. Or hydrodynamic order, which could be a good candidate. Now let's apply to Euler. So for this 3D flow, we went from this ordered structure at t equal to 0 to t equal to 60. We just compute the thermodynamic, the hydrodynamic entropy. Thermodynamic entropy is constant, so I don't need to worry about it. It's constant. So in here, this S hydrodynamic entropy is increasing and it saturates to the maximum possible value. You can compute the maximum possible value; it reaches there. Great. So I think it's thermalized. It's a good signature, and it goes there. But what about 2D? So 2D, these are 3 runs. So we look at 3D and we find that till t equal to 30, we can see, well, these are initial transients, but there is a region where it is decreasing with time. For all the 3 runs, this part blue is not, is also, I mean, it's kind of fluctuating a bit, but it's decreasing. So here order is system is getting more ordered or entropy is decreasing with time. And if you run it for a long time, this is somebody generated this till 1000, it is kind of, there is some decrease here. I believe it is not yet saturated. That means we need to even go further down, but it's almost saturated. It's almost reaching asymptotic value, but it's getting more ordered. I mean, this picture is telling us that system is getting more ordered with time, which is a shocking thing. That how can isolated system get more ordered with time? It's not counter to second law, because thermodynamic entropy is constant, but the hydrodynamic entropy is decreasing. So despite 2D system being isolated, I think this is a kind of surprise for us, but okay, anyway. So I just want to take a little bit more time. I think we have enough. So let's look at this hydrodynamic picture a bit more from a microscopic perspective, and we can relate it to arrow of time. So it does make sense to me, and I just want to mention this here. So again, going back to our this macroscopic system, we have a lot of molecules and they're all moving around. So we are going to look at a hydrodynamic system where there is a certain coherent motion, this vortex motion. So this coherent motion, we are going to write down the energy of this. We assume the ballistic interaction or short range interaction for the molecules. So total energy is conserved. In fact, total energy is essentially kinetic energy, is ballistic. So that's what we'll assume. So this is the total energy, half mv squared. A is the label of the particles. So all these particles are interacting, and now, but this part we can separate the velocity field into two components. One is hydro velocity and one is fluctuating velocity. Okay. So we have, I mean, for the atmosphere, like 1 meter per second, which is the like wind motion, it is that, and the sound speed will be the fluctuating thermodynamic velocity. So we substitute it here, then I'm going to get one kinetic energy from the hydro part and one kinetic energy from the fluctuating part. Straightforward, there is nothing more complicated. Now, what really happens in this flow? In fact, it's obvious what happens in the flow is that this part, the hydro part, is isolated system. I'm not forcing anything. Is basically total energy is conserved. But in hydro part, this part decreases with time, but thermo part increases with time. Okay, the thing's energy basically gets into heat, but heat is nothing but thermal energy. Total energy is constant. So we are converting the coherent hydrodynamic energy to incoherent energy. That is what is being done in this isolated system. So friction is basically the interpretation of conversion from here, conversion from coherent hydrodynamic energy to incoherent energy. So viscosity is basically this interpretation. Now, is general, of course, we talk about it in StatMech, but this connection with hydro, this is what we get very nicely. So Kolmogorov flux will come from this part, Kolmogorov flux, and this part is getting heated, quasi-equilibrium. That's what is the case. So, so dissipation, to me, we say that fundamental forces are all four of these: gravity, electrodynamics, nuclear. But friction is natural in multi-particle systems. So this system, friction is basically natural. Of course, we model this part as a new Laplacian. Okay, but this is, I think, this is a nice way to look at what is happening in the systems. And this part can show difference in order. I mean, this is, I think that's what we need, multi-scale entropy. I think the entropy of usual entropy is only the microscopic entropy. So this part probably should be, we should do more. Now coming to, so since it's a friction, then we can define arrow of time in an isolated system. For Euler turbulence in 3D, system is getting order to disorder because there's a flux, and that is defining arrow of time, though it is an isolated system. We don't need entropy, thermodynamic entropy, because thermodynamic entropy for Euler is constant. So here we can use this energy flux idea to define arrow of time. So it's a, typically we use entropy as a measure for increasing entropy, but some systems probably it is not, I mean, not probably, this is an example. The thermodynamic entropy is not really giving us a clue which way the time is moving. So I'm just going to give a short introduction to arrow of time. So, so some students who may not be kind of know this problem very well. So fundamental forces respect time reversal symmetry. So like gravity, Newton's laws without friction will T going to minus T and V going to minus V will respect this equation remains unchanged. Okay, so that's called, these forces do not give the direction of time. Okay, and this is true for almost all forces except weak nuclear. Weak nuclear does violate this time reversal symmetry. But let's focus on these, only gravity. Okay, this is to keep life simple for a short introduction. So the example is here. So a particle going forward in time, ballistic, a particle ballistic. Okay, I'm not thinking of a bomb or something. It's just particle is going down. Now, if I reverse this particle at the final step, idea is that to see whether the system is reversible or not, what we do is we will let the particle go. So let me just make this part is important to highlight. So we have a particle going like that, forward motion. Now we are going to, so it comes here. So this is forward motion without friction. Now I'm going to change the velocity here, reverse the velocity. So reverse the velocity, then without friction is going to come back to the original spot. Now this is a reverse motion, which I do it in a video. But is this possible? Is it realizable in real world? It turns out this system is realizable. If I just shoot the projectile from here, it is going to follow the trajectory. So the time reversed motion is not differentiable from the real experiment. Or if I do a real experiment, I can see that I cannot say that this movie which is reversed is a fake video. So we have to realize whether it's a fake video or a real video if it's reversed. If you can identify that reverse video is a fake video, then we know that time reversal symmetry is broken. But if you cannot, then it is respected. So let's look at in real life. So I took a clip from a movie. So I will ask you to guess which movie this is from. Okay, this is a forward one, no? I mean, this is the forward. I reversed the movie. Definitely, we can see that it is reversed. If somebody showed that this is really a movie, but we'll say, well, it's not the real movie. It's a reversed film. So I can differentiate forward and backward. In all our real life, you can differentiate forward and backward. So macroscopic systems, there is a direction of time. Now, this is just for fun, okay? I mean, I know everybody knows about it. Anybody want to make a guess which movie this is from? From, of course, international audience, you won't know which movie, but anyway, that's for the later. But normally we say that entropy is will give us direction, right? So system entropy increases with time, and great, that will give the direction of time. But in hydrodynamic systems where entropy is questionable, for Euler I showed that entropy is not defined, thermodynamic entropy, then what should I do? So one idea is to use the energy transfer, energy flux. Okay, so in turbulence, the energy goes from, in 3D turbulence, energy flows from large scale to small scale. Now, if I reverse the movie, then what can I say that can identify the reverse movie by computing the energy flux? Okay, I just reverse the movie and then I compute the energy flux. What will I get? In fact, you can make a guess that energy will flow from small scale to large scale in 3D. Okay, and that is, if you compute it, then you can say it's a fake video because energy is going from small to large. We can identify it by doing real computation. So we can use cosmograph P41. So this is our structure function, and U cube is minus 4/5 epsilon r, right? This has been told many times. But in a reverse movie, so I just play the movie backwards, then what happens to the velocity field? U goes to minus U. I substitute it here. So the left hand side will change sign. It becomes negative. So I'll get negative becomes positive, and I'll get this. So my flux epsilon, to interpret flux, epsilon will become negative. And that means we can clearly identify this to a fake video. So that means I can see by looking at a frame. I don't need the full video. I just look at a frame. For forward movie and backward movie, will have different energy flux. And that is a good measure to get the arrow of time. So we can use this for define arrow of time, and we can contrast these two flows. So I think this is another way to look at energy flux and arrow of time. So by the way, though it is for hydrodynamics, I can argue that this also will work for many other systems. Okay, let's look at a biological system. So I take food at large scale, no? I take food in my mouth, and this energy goes from the food to the cells, not vice versa. So energy transfer is happening in one direction. It is not happening in other direction. In the universe, there's a Big Bang. Energy flows from the Big Bang. Well, if you don't believe in Big Bang, or say, well, it's too complicated, you can say supernova explosion. There's energy flowing from supernova explosion and doing a lot of stuff, including magnetic field generation. So there is the energy transfer in almost all natural systems. In earthquake, there is energy transfer from large scale tectonic plates to small scale of ruptures of stuff. So this seems to be one of the things in nature. 2D has certain trick, but which I will not discuss it here. If there's a question, I'll answer it. So we can use this idea to define arrow of time. So the title of the paper was Asymmetric Energy Transfer in Non-Equilibrium Systems Can Define Arrow of Time, or something of the sort. So it just should be non-equilibrium forced system. So intuitively speaking, so we have energy coming at large scale and dissipation at small scale. So if something is coming at large scale and there's dissipation, it just creates a channel. And that seems to be a generic pattern in many systems where supply energy at large scale and there's a sink at small scale, and that will create a direction. 2D is an exception. So I will conclude. I have enough time for Q&A if at all. So 3D Euler thermalizes, its entropy increases with time. Hydrodynamic entropy. Thermodynamic entropy was constant. In 2D Euler, it's out of equilibrium, and its entropy, hydrodynamic entropy, decreases with time. Not all the time, but there is a significant period where entropy decreases with time. And isolated system can become ordered with time. And I think this is an interesting observation, especially for quantum. There's a lot of discussion on this topic. So self-gravitating system also, I think, would be important. System in the same category, because self-gravitating systems do become ordered, I believe, which is, yeah, so that could be another way where we can apply these ideas. And arrow of time by energy transfer could be a good way to, well, energy transfer can be a good measure for arrow of time. Okay, I'll end here and I can take questions. Thank you.
Thank you so much, Dr. Mahendra Verma. Start with questions.
Can I ask you a question, sir? Yeah, it is a very interesting talk. See, 2D Euler turbulence is out of equilibrium, and then that is initially you have 2D Euler. Of course, 2D is not real. In real life, there are no 2D systems at all. 2D flow, particularly in fluid mechanics, I mean, it's really an ideal situation. But why it, see, 2D Euler reaches, I mean, it does not go out of equilibrium is because of mixing. Mixing is the thing. You have 2D Euler, you have something.
No, I disagree. I mean, there's no mixing here. I mean, where is the mixing?
No, 2D Euler, you have large scales. You showed some large scale structures, and then it will mix, and so it can generate.
No, first let me answer this. First, 2D systems, really, of course, 2D system does not exist, but it's a good idealization for formation of hurricanes. Okay, so 2D systems are used in physics quite often, and I think this is a good model for rotating turbulence. It's not, of course, same as this, but it's a good model. Coming to mixing, well, I would say this property, which is the formation of structures, is because of the nonlinear interaction, is nature of interaction. Nature of interaction.
Yeah.
So there is a tendency to inverse cascade, which is happening here. There's a tendency for the systems to kind of create structure. 2D, we know it from hydrodynamics, Khanin theory, that there's inverse cascade, and that leads to the formation of structure, which is playing here. It's not too surprising that we are getting it to be non-equilibrium. Only thing was that we set viscosity to be 0, and it worked. So we were making a guess that should happen, and it kind of, we saw it, yes.
Sorry, can I answer?
Yes.
Asked you earlier,
Did you try running much smaller system sizes like 64 squared?
Yeah, so I remember your question to Sandeep. Sandeep is on it.
Okay.
First thing we did was to run it for a long time to see that it is
Sure.
not
Right.
thermalizing. Yes, we want to do it with different
Okay, there's
scale.
another related question is, can you, I assume you can, calculate a correlation function? So U of K and T, U of K,
T plus
T
tau.
plus tau.
Yes, yes.
And that will, from it, you can extract a K-dependent relaxation time.
Right.
Now, is it that at small K, that relaxation time is becoming very large? I mean, you can check it by
Yeah,
calculating it. It might
Great.
be, it
Thanks
might
for
not.
the suggestion. It's a
Okay.
good suggestion. Yeah.
Okay.
We look at
That's
it.
all.
That would have information about cascades. Yes.
Thank you.
Thanks. Thank
Yeah, thanks a lot for the talk. Mahendra.
you. Yeah.
I had two probably very basic questions.
Yes.
One was for your definition of that P of K.
Yeah.
Is it not, is the E of K not weighted by K itself?
This was a modal energy.
Right.
So no, it is not weighted. So modal energy by total energy is P of K for a given mode K.
Okay. Okay. So that's the total energy that you use. The other is, I mean, of course, do you think there are other ways to define hydrodynamic entropy, in which case it might go up? For instance, the three initial conditions that you showed, it seemed like there was a very high wave number initial condition, but then your energy spectrum, of course, is more energized, and there are many modes that have energy.
Right.
So from that sense, you need more information to quantify your system, right?
Yes.
So it could seem that the entropy has increased in that perspective.
Yes, so Somdeep is kind of pressing that we can use, instead of EK energy, but you can use entropy by total entropy. Entropy, sorry, total entropy by total entropy per mode by total entropy. And that's another measure. Yes, so it's not a unique measure. And to just tell you the background, that entropy based on entropy is increasing with time, because the large Fourier modes are getting thermalized. So yes, but if you're looking at coherent structures, they're typically at small wave numbers, the ones which have more energy. So this measure, which I proposed, is good for quantifying the structures, which has more energy. So more energy structures, if they have more energy, then you can use this, but it's not unique. You are right about that.
Thank you. Thanks a lot.
Let me continue. See, I have got to follow up on the question I asked.
Okay.
See, when you talk about 2D turbulence, if you have, depends on the scales you are talking about. If you have very large scales, then it is difficult to get equilibrium, because the two modes, whatever be the, whether it's fluid mechanics or structures or whatever it is, if the modes are very close to one another, then they will normally, generate other modes, other frequencies.
Mhm.
So if the modes, as the other gentleman was telling, if the modes are very far apart, then it will just become a single mode. So you will get equilibrium. See, one will override on the other, and it's a nonlinear system, simple interaction of nonlinear dynamics, dynamical system phenomena.
Okay.
So what I mentioned was, in a 2D system, the mixing, if the scales are close by, within, say, about 3 decades or so, then it can generate a non-equilibrium system. But if the scales are far apart, if you take vortices in a 2D system, which are far apart, then it will reduce to equilibrium, say, higher orders, higher mode, higher order, lower order, large scale mode.
Okay, we'll explore.
There aren't any more questions. Let's thank our speaker again.
Hello? Yeah. So you told that from the equilibrium system, you are converting it to a non-equilibrium system by using some coherent kind of motion. So that
Maybe ask your question and complete your question, then.
So that coherent kind of motion, whatever is in the system, you told that this could be an ideal model for rotating turbulence.
No. So let me just say it properly. Maybe I didn't communicate it well. So depending on the initial condition, a system can go to equilibrium or non-equilibrium.
Okay.
So if you start with random initial condition, which is white noise, then it remains in equilibrium. Is okay.
So
3D.
how the coherent motion has been created?
Yeah, so in 3D coherent motion, if you start with, it goes to equilibrium by shown by Brashe's group, but in 2D it does not. 2D, because of the nature of interaction, is the nature of the system. Inverse cascade plays a role. It
Okay.
tends to remain non-equilibrium. It is out of equilibrium, so that is one point. So you have to look at system by system. Quantum systems, do they thermalize or do they not thermalize? So it depends on system whether it could thermalize or non-thermalize. Secondly, I just made a remark about rotating turbulence, like 2D systems, 2D hydro, a quasi 2D hydro. Well, rotating, if you rotate very fast, then their fluctuations along vertical directions are suppressed, and they tend to become like hurricane-like structures. And it can be approximated by quasi 2D systems. That was my remark. Nothing more extraordinary. It is known.
No, actually, I was like rotating is something kind of external forcing, and this
Yes.
Euler equation do not have any.
Yeah, no. So this
no
was
force.
a tangent remark, not connected with Euler. It wasn't connected with Euler.
Okay, thank you.
Thank you.
If I can make a comment about the coherence system, see when you have
Maybe we can wrap up the session and we can talk offline. Thank you so much again, Dr. Verma. Thank you.